Hello everyone, this is Dennis and you are on the Den Electro channel. Today I want to show you one of the easiest ways to get 24 volts from the computer power supply. It is not necessary to heavily redo the circuit or rewind the transformer. For this, the 24 volt winding is already there. You just need to know where she is. The power supply unit outputs several different voltages, but we will only need two, +1, 2, and -12 volts. They can be used together, and in total these voltages will give the desired 24 volts. But there is one problem. Although in a transformer these voltages are taken from one winding, a large current can only be removed from the +1, 2 lines. On the -12 line, the current is 10 times less. This is due to the fact that the +1, 2 volt line is very actively used, while the -12 line is not. Because of this, all the parts on the +1, 2 volt line are powerful, and on the -12 weak line. But if these parts are replaced, then it will also be possible to remove large currents from the -12 volt line, more than 10 amperes. Fortunately, there are a few of these parts: a capacitor, a choke, and rectifier diodes. Now I'll show you where they are, replace them, and then test the power supply under load. To make it easier to work, the power supply must be disassembled. We solder all the wires from the mains power connectors, unscrew all the bolts, pull out the cooler and the board. The power supply is controlled by the AT2005V microcircuit. There are 5 types of voltages in the power supply. The orange wires are 3.3 volts. The red wires are 5 volts. The black ones are a common negative for all voltages. The yellow ones are +1, 2 volts. The white ones are -5 volts. And at the end, the blue wire is -12 volts. The declared power of the power supply unit is 350 watts. The +1, 2 volt line is designed for 14 amps, and the -12 volt line is only half an ampere. In a transformer, the windings are arranged as follows. The secondary winding consists of 2 semi-windings. To obtain a voltage of +1, 2 volts, only 1/2 cycle is rectified from each winding. For this, a diode assembly with a common cathode is usually used. The current passing through here is very huge, and therefore Schottky diodes are usually used here to reduce losses on diodes. The common negative, or as it is correctly called, ground, will be located at the midpoint of the secondary windings. Current ripples are smoothed out by an electrolytic capacitor and a smoothing choke. There is also a group stabilization throttle in this line. There are a lot of windings in it, all voltage lines pass through it. 2 more diodes, a choke, a capacitor, and also a group stabilization choke are used to generate the -12 volt voltage. Only unlike the +1, 2 volt line, conventional pulse diodes are used here. Designed for a small current of only 1 or 2 amperes, and they are not assembled, but separately. Thus, there will be a voltage of 12 volts between the +1, 2 volt pin and the ground. And there will also be a voltage of 12 volts between the ground and -12 volts. If you take a good look at the secondary winding of the transformer and all 4 diodes, it becomes clear that an ordinary rectifier bridge is assembled from them. The output of the plus from the diode bridge will be on the +1, 2 volt line, and the minus on the -12 volt line. Therefore, the total output voltage will be 24 volts. That's exactly what I'm going to be testing. The load will connect to the plus and minus. Now you need to turn on the power supply, but to do this, it is not enough to apply voltage to it. In addition, 2 contacts must be connected on the ATX connector. We take a good look at it. Look at which side the latch is located and find the PS on contact on it. This is usually a brown wire, and we connect it to any black wire, the minus. If you have a 20-pin connector, then this pin will be on the 14th pin. And if it is 24 pins, then it will be on the 16th pin. The current and voltage here are small. You can even use a thin bare wire. After that, the power supply unit should start. Now we need to find the +12 volt and -12 volt lines and see what the voltage between them will be. I'll start with the Molex connector. First, I insert the negative probe into the black wires. There is a common negative. And I attach the positive probe to the yellow wire, where the line is +12 volts. Everything is right. I'm leaving the black dipstick in place for now. And on the ATX connector, I attach the positive dipstick to the blue wire, where the line is -12 volts. The voltage here is almost -11 volts. Now I'll look at the total voltage from the two lines. To do this, I will insert the plus probe into the +12 volt line, where I will have a plus. And I'll attach the minus dipstick to the blue wire, where I'll have a minus. As expected, the total voltage is almost 23 volts. My power supply, like many others, uses FR157 diodes on the -12 volt line. These diodes can withstand a high voltage of 1000 volts, but the current is only 1.5 amps. Instead, I will put the SR5100 shock diodes. They are designed for a current of 5 amps and a voltage of 100 volts. The pulse diodes D3 and D4 are located here. They are located right next to the Schottky diode assembly. I already wanted to replace them, but then after a thorough inspection of the circuit along the -12 volt line, I found another diode. It was located under the group stabilization throttle. To get to him, I had to solder off a nearby capacitor. I did not completely solder all 3 diodes, but pulled out only one leg at a time. It turned out that a diode of unknown purpose was installed here. Just like diodes D3 and D4, this is an ordinary FR157 pulse diode. As a result, I had to replace not 2 diodes as I wanted before, but 3. The result is such a design. I soldered another wire to the -12 volt line so that the cross-section was larger. With +12 volts, I will also take 2 wires. I decided to turn on the first time after this small change through a light bulb. You never know, I might have messed up something. After plugging in the power, the light bulb blinked and went out. This is a good sign. Now I will increase the load. I'll see how much current the power supply outputs and how much the voltage drops. At a current of 0.3 amperes, the spiral of the light bulb began to glow. With a current of 0.5 amperes, the light bulb began to glow even more. It became clear that the power supply is working, and therefore the light bulb can now be removed. Now I load the power supply again, but without the safety light. If something goes wrong, then no one can save the power supply. With a current of 2 amperes, the voltage dropped by almost 1 volt. The diodes have been warm for a long time. This is especially true for the D5 diode. This is the diode that performs an unknown function. I load further. The current is 4.5 amps. The voltage has dropped to 21.7 volts. Then I decided to try to reduce the voltage drop. To do this, you can add a small load to the 5-volt line. I will connect the additional load to the Molex connector. As a load, I use a 5 ohm resistor with a radiator. The current it consumes will be about 1 ampere. The resistor will heat up very much, and 5 watts of heat will be dissipated on it. How much this useless load will help us, we'll see now. I'll load the power supply again. The voltage is 22.5 volts. The current is 2 amperes. The load is just over 40 watts. I connect a resistor to a 5-volt line. The voltage went up by 0.4 volts. I disconnect the resistor and the voltage drops again. In general, as you have already understood, this life hack did not help me much. Adding a 5-watt load to raise the voltage by half a volt is somehow irrational. But anyway, I'll leave it for tests for now. I'm lifting the load further. The diodes are already decently heated. The voltage is 22 volts, and the current is 5.2 amperes. The load is about 110 watts. The voltage did not drop much, and therefore I believed that the power supply unit had a reserve of power. The load can be increased further. But the diodes that I have installed have almost reached their limit, and therefore they need to be replaced. In parallel with diodes D3 and D4, I installed one more of the same diode, and instead of diodes D5, I installed a 20100 CT diode assembly. These are twin Schottky diodes, and they can be installed on the radiator. They can withstand a current of 20 amps and a voltage of 100 volts. Now the design looks like this. Now the voltmeter shows almost 24 volts. Due to the fact that I removed the pulse diodes and installed the Schottky diodes, the voltage became a little higher, since the voltage drop across them is less. With a current of 2 amperes, the drawdown is 1 volt. Then, in the same way, as the current increases, the voltage continues to sag. The voltage is slightly more than 22 volts. The current is 4.5 amperes. The wires are a little warm, but the pulse diodes are already hot. The assembly of Schottky diodes is also a bit warm. I'll try to load it even more. The voltage is almost 22 volts, and the current is just over 6 amps. The load capacity is more than 130 watts. The pulse diodes are already very hot. The Schottky diodes have already warmed up too, but the finger does not burn. I'll add some more load. The voltage is 21.5 volts. The current is 7.1 amperes, which is just over 150 watts. After that, the smell of molten plastic began to emanate from the power supply. Because of this, the experiment had to be completed. I found out the reason for the smell almost immediately. The problem was this. The L3 throttle has warmed up. This is the throttle that smooths out ripples on the minus 12 volt line. The shrink tube that is on it started to smoke. This choke is wound with a very thin wire, as the entire line is designed for low current. In addition, the throttle of the group stabilization has warmed up. To be precise, not the entire throttle got hot, but only the core that is connected to the minus 12 volt line, and the heat coming from it warmed up the entire throttle. Of course, the throttle heats up from the plus 12 volt line, but the wire there is much thicker. Then I decided to make the last changes. remove the SR5100 single diodes, and instead of them, as well as instead of the D5 diode, put 20100CT Schottky diodes, which can be attached to the radiator and not be afraid that they will overheat. I'll remove the useless D5 diode and make a jumper instead. By the way, if you know what it was needed for, then write in the comments. I will also replace the L3 throttle made of thin wire, and instead I will put a larger throttle with a large cross-section wire. After reworking, the scheme will look like this. Diodes D3 and D4 now look like this. Each consists of two and is located on its own radiator. The L3 throttle took the first one. This self-made choke is wound with a thick wire on a core taken from an energy-saving light bulb. Of course, this throttle is very large, and if you want to install it on the board, you can take something smaller. I did not measure its inductance, but it is advisable to take the same as the old one. If you do not have an inductance meter, then you can make it yourself. There is a link in the description. I'll take this thing for extra load. This is an ordinary box, and inside there are nichrome coils from the heater. There are wires tied at different distances. By connecting different wires, you can change the load power. To prevent anything from burning, the fan blows through the box from the processor. I connected the heater via this arrow ammeter. On it, we will see how much current the heater consumes, and we will also look at the voltage on the electronic load. At idle, the voltage is 24.3 volts. After removing one diode from the circuit, the voltage became slightly higher. In theory, under heavy load, the voltage drop should also decrease. I connect the wires and turn on the heater. The current is 4.5 amperes. The voltage dropped by 1 volt. The load is slightly more than 100 watts. I increase the load further. There are slightly more than 4 amperes on the switch ammeter, 7.1 amperes on the electronic load, and a total current of 11 amperes. And the voltage is almost 22 volts. The total load capacity is 240 watts. The radiators are already a little hot. The throttle of the group stabilization is hot. The blue thing is that the wire along the -12 volt line is hot in it. The finger does not burn the entire area of the drop, but only in some specific places, where that thin wire runs. I think if there wasn't a fan nearby, the varnish on the wire would have already started to melt. Now I'll take a multimeter and see what voltage is on each line. I have already connected the negative probe to the midpoint of the secondary winding. The voltage on the +1,2 line is 11.4 volts. There are 10.3 volts on the -12 line. Here the drawdown is greater, but it is understandable, and the wire is thin in the throttle and tracks on the board. In addition to all these alterations, the C2 capacitor can also be replaced. On the +1,2 volt line, its capacity is 2,200 microfarads, and there are only 470 on the -12 line. Due to the increase in current, voltage ripples could appear on this line. Big the capacity should reduce them. As you can see, it is very easy to find 24 volts in the power supply and remove more than 10 amps from them. But keep in mind that everyone's power supplies may be different. They use different chips, and the total power of the power supplies may also be different. If the power supply is very weak, for example 200 or 250 watts, then you will not be able to remove 10 amps from the 24 volt line. The maximum that can be squeezed out there is about 70% of the total power of the power supply unit. After that, the voltage will start to drop significantly, the power supply will go into protection, and simply turn off. That's all for today. Please like, subscribe to my channel if you haven't subscribed yet, Ask questions in the comments if someone doesn't understand something. And for now,